Good afternoon. There's a medical revolution happening all around us, and it's one that's going to help us conquer some of society's most dreaded conditions, including cancer. And the revolution is called angiogenesis, and it's based on the process that our bodies use to grow blood vessels. So why should we care about blood vessels? Well, the human body is literally packed with them, 60,000 miles worth in a typical adult. End to end, that would form a line that would circle the Earth twice. The smallest blood vessels are called capillaries. We've got 19 billion of them in our bodies. And these are the vessels of life. And as I'll show you, they can also be the vessels of death. Now, the remarkable thing about blood vessels is that they have this ability to adapt to whatever environment they're growing in. For example, in the liver, they form channels to detoxify the blood. In the lung, they line air sacs for gas exchange. In muscle, they corkscrew so that muscles can contract without cutting off circulation. And in nerves, they course along like power lines, keeping those nerves alive. And we get most of these blood vessels when we're actually still in the womb. And what that means is that as adults, blood vessels don't normally grow, except in a few special circumstances. In women, blood vessels grow every month to build the lining of the uterus. During pregnancy, they form the placenta, which connects mom and baby. And after injury, blood vessels actually have to grow under the scab in order to heal a wound. And this is actually what it looks like, hundreds of blood vessels all growing towards the center of the wound. So the body has the ability to regulate the amount of blood vessels that are present at any given time. And it does this through an elaborate and elegant system of checks and balances, stimulators and inhibitors of angiogenesis, such that when we need a brief burst of blood vessels, the body can do this by releasing stimulators, proteins called angiogenic factors, that act as natural fertilizer and stimulate new blood vessels to sprout. And when those excess vessels are no longer needed, the body prunes them back to baseline using naturally occurring inhibitors of angiogenesis. Now, there are other situations where we start beneath the baseline and we need to grow more blood vessels just to get back to normal levels, for example, after an injury. And the body can do that too, but only to that normal level, that set point. But what we now know is that for a number of diseases, there are defects in the system where the body can't prune back extra blood vessels or can't grow enough new ones in the right place at the right time. And in these situations, angiogenesis is out of balance. And when angiogenesis is out of balance, a myriad of diseases result. For example, insufficient angiogenesis, not enough blood vessels, leads to wounds that don't heal, heart attacks, legs without circulation, death from stroke, nerve damage. And on the other hand, excessive angiogenesis, too many blood vessels, drives disease. And we see this in cancer, blindness, arthritis, obesity, Alzheimer's disease. In total, there are more than 70 major diseases affecting more than 1 billion people worldwide that all look on the surface to be different from one another, but all actually share abnormal angiogenesis as their common denominator. And this realization is allowing us to reconceptualize the way that we actually approach these diseases by controlling angiogenesis. Now, I'm going to focus on cancer because angiogenesis is a hallmark of cancer, every type of cancer. So here we go. This is a tumor, dark, gray, ominous mass growing inside a brain. And under the microscope, you can see hundreds of these brown-staining blood vessels, capillaries, that are feeding cancer cells, bringing oxygen and nutrients. But cancers don't start out like this. And in fact, cancers don't start out with a blood supply. They start out as small, microscopic nests of cells that can only grow to 1/2 a cubic millimeter in size. That's the tip of a ballpoint pen. Then they can't get any larger because they don't have a blood supply, so they don't have enough oxygen or nutrients. And in fact, we're probably forming these microscopic cancers all the time in our body. Autopsy studies from people who died in car accidents have shown that about 40% of women between the ages of 40 and 50 actually have microscopic cancers in their breasts. About 50% of men in their 50s and 60s have microscopic prostate cancers. And virtually 100% of us, by the time we reach our 70s, will have microscopic cancers growing in our thyroid. Yet without a blood supply, most of these cancers will never become dangerous. Dr. Judah Folkman, who was my mentor and who was the pioneer of the angiogenesis field, once called this cancer without disease. So the body's ability to balance angiogenesis, when it's working properly, prevents blood vessels from feeding cancers. And this turns out to be one of our most important defense mechanisms against cancer. In fact, if you actually block angiogenesis and prevent blood vessels from ever reaching cancer cells, tumors simply can't grow up. But once angiogenesis occurs, cancers can grow exponentially. And this is actually how a cancer goes from being harmless to deadly. Cancer cells mutate, and they gain the ability to release lots of those angiogenic factors, natural fertilizer, that tip the balance in favor of blood vessels invading the cancer. And once those vessels invade the cancer, it can expand, it can invade local tissues, and the same vessels that are feeding tumors allow cancer cells to exit into the circulation as metastases. And unfortunately, this late stage of cancer is the one at which it's most likely to be diagnosed, when angiogenesis is already turned on and cancer cells are growing like wild. So, if angiogenesis is a tipping point between a harmless cancer and a harmful one, then one major part of the angiogenesis revolution is a new approach to treating cancer by cutting off the blood supply. We call this anti-angiogenic therapy, and it's completely different from chemotherapy because it selectively aims at the blood vessels that are feeding the cancers.